Assalamu alaikum, my dear students of Pharmaceutical Organic Chemistry II. Today, inshallah, we are going to handle a new topic which is about qualitative determination of amines. In today's experiment, we are going to test the salt formation properties of amines. As we know from the theoretical part of the practical session, that amines are basic nitrogen-containing compounds. They are all derived from ammonia, and the hydrogens of the ammonia are substituted by different alkyl or aryl side chain, which later will define more physical and chemical properties of the compounds. Okay, for today's sample, we have tyrosine, para-amino benzoic acid, paracetamol, and diethylamine. All of them contains nitrogen, so we can classify them as amino-containing compound or simply amines. Let's draw the chemical structure of each of them before we proceed. Let's start by tyrosine. We know that tyrosine, one of the amino acids, so it contains the functional group, which is carboxyl group, and amino group. In addition to that, it is linked to benzene ring, very characteristic benzene ring. So this benzene ring, for sure, it will reduce the solubility of the tyrosine powder, as we are going to see later on. For the para-amino benzoic acid, it's once again contain benzene. And when we say benzoic acid, it means again it contains carboxyl group and it contains amino group. For the paracetamol, once again, it contains benzene ring in addition to hydroxyl group linked to the amino group, as we can see here. For the diethylamine, it's very simple structure. Actually, it is one nitrogen and the three hydrogen, one of them is substituted by ethyl side chain and the other, once again, substituted by ethyl side chain, while this hydrogen is still intact as it is. Okay, for the reagent, we are going to use distilled water, which is simply HOH or H2O. For hydrochloric acid, it's very easy. And for the sodium hydroxide, these are the reagent we are going to use today. The instruments, we are going to list them a few minutes after we proceed with this worksheet overview. Okay, how we are going to proceed with the practical? We are going to take 0.25 gram of the amine, which are one of our samples. If the sample is liquid, as in case of diethylamine, we will take 0.5 ml. And we will place them in a test tube, then we will add 2 ml of distilled water. The aim of this step is to test if the amino-containing compound are water-soluble or water-insoluble. As we explained in the theoretical part of the practical, all the amines by nature, if they are derived from ammonia, so they will be water-soluble. But the physical property or the solubility will be determined by further characterization of the adjacent side chain. If the side chain contains long chain hydrocarbon side chain, or if it contains benzene ring, so for sure this will reduce the solubility of the amine in the water or in the aqueous solvent. Okay, so after this step, we are going to see if the sample is water insoluble, we are going to proceed further. If the sample is water soluble, so we will not proceed, and this will occur in the case of diethylamine. Okay. If the amine is water insoluble, we are going to proceed to the next step, which is we will take the sample, the same quantity, and we will try to add to that HCl or hydrochloric acid solution of a concentration 1 molar, but in dropwise way. We will find that the amine, whatever the amine, is going to react with HCl. So it will form a salt. It's a simple acid-base reaction. And the salts, most of the salts of the amines, they are water soluble. So after addition dropwise of HCl and shaking, we will find that most of the amines, they become soluble. Okay. Later on, we are going to reverse this reaction by addition of 2 molar sodium hydroxide. This test, it would be called as solubility test of amine, and this one the solubility test of amines salts, and this one we will call it a reprecipitation test. Why we call it a reprecipitation test? Because actually the amino containing compound, after reaction with HCl, it will form a salt, and this salt, upon addition of sodium hydroxide, it will return back into the precursor amine. So it means we will reprecipitate again, as the precursor amine are water insoluble. Then we are going to write the results in this sheet Here we have to write the solubility result in the distilled water, and here we have to write the solubility of the salt formed after reacting with HCl. This is the ionization or the deionization of amines in the aqueous solution. And then we are going to proceed with the reprecipitation test by addition of sodium hydroxide solution. As we can notice here, this is the general structure of the amines. After addition of HCl, it will give us the salt, which is the amine hydrochloride. This amine hydrochloride salt, it is water soluble. But after addition of sodium hydroxide, we will return back to the same amine. If you notice, it would be the same precursor amine, which is in this case water insoluble, and once again it will return insoluble. Then we are going to proceed with writing the chemical equations, and I will simplify it for you by writing only one chemical reaction, one full chemical reaction between one of the samples and the HCl and sodium hydroxide solution. Later we will draw the conclusion. So now let's proceed to the practical experiment. Before proceeding in this practical experiment, we have to make sure that we have all the required chemicals and instrument needed. We will start by having paracetamol powder, para-amino benzoic acid powder, tyrosine powder, and all the powders are placed inside petri dishes in front of each powder sample. In addition to this spatula, we will need test tube rack, test tubes of capacity between 10 to 25 milliliter, plastic droppers, diethylamine sample solution, sodium hydroxide solution of a concentration 2 molar, hydrochloric acid solution of a concentration 1 molar, in addition to the distilled water and distilled water dispenser. Now we are going to proceed. Okay, before proceeding with the chemical experiment, once again we have to make sure that we are putting all the personal protective equipment, including the gloves and the goggles. So here we go. We will start by labeling the test tubes with the samples we are going to use. So I have here paracetamol, and then I have para-amino benzoic acid, and here I will have tyrosine, and then I will have diethylamine. Okay, now let's put these labels here. Usually when we label the test tube, we prefer to label it on the top position or in the apical part of the test tube, so later if we need to do boiling or any reaction, this piece of paper will not just be dispatched into the water bath. Okay, and tyrosine. Here we go. Thank you, Mr. Tyrosine. Okay. And then diethylamine. Okay. Okay, so now I have my test tubes labeled. So I will start by putting the sample in each test tube. So I will start by paracetamol. I will have small amount, which is equivalent to 0.25 gram. Paracetamol, and then para-amino benzoic acid. Of course, I have to use different spatulas for different sample to avoid cross-contamination and to make sure that the result is yielded from that particular chemical, not from any remnant from the previous one. Okay, and diethylamine, it's liquid, so I will take around 0.25. Okay. Now we are going to add to this distilled water to make sure that if it is soluble in water or not. Okay, so now we are going to add distilled water, around 2 ml. So this is for paracetamol. Of course, we have to shake it gently to make sure that these particles will not be lost up there. For 20 seconds. it's very obvious that it's not soluble in water. So this is for paracetamol. Let's check for para-amino benzoic acid. It's once again not soluble. Okay, so let's go to the tyrosine. Yeah, it's very apparent that it's not soluble. So let's now go with the diethylamine, which is liquid in nature. For sure, to know if the liquid is soluble or not, we have to check if it will form two layers or just a single layer. If it will form two layers, it means it is not soluble, but if it is one single layer, it means it is soluble. So now, if you can see, if you can check it, I will see in the camera if you can see it or not. It's very apparent that it is one layer. So it means that diethylamine is soluble in aqueous media. So we will exclude the diethylamine from today's experiments, and we will proceed with the other three samples. Of course, we have to make sure that we write down all the result we got, so we will not forget anything. So I will write here the samples we have, which were tyrosine and para-amino benzoic acid, or simply BABA, and paracetamol, in addition to the diethylamine. For the aqueous solubility, tyrosine is insoluble, while para-amino benzoic acid, once again, it is insoluble. For paracetamol, it is insoluble, while for diethylamine, it is soluble. So this is for the aqueous solubility. Now we are going to proceed with the salt formation test. Okay, for the salt formation test, once again, we will have our test tubes, the paracetamol, and I will take the same quantity, which is 0.25 gram. This time I'm going to react it with HCl. So we have to find out what would be the results of reaction between amines, which are the basic compounds, and the HCl, which is an acidic compound. I think it would be simple acid-base test, acid-base reaction. So we are going to see that right away. Where is the HCl? Yes, here it is. So paracetamol, we are going to add, let's say, 1 ml in the beginning, and then dropwise till complete the solution. If you can see, with the first sample, which is paracetamol, the amount of paracetamol decreased. Okay, I can see now it's clear for you, but it's not totally soluble, so we have to shake it for longer time, or we can simply add this amount of HCl. If you are going to compare the result here with the result before with the distilled water, the aqueous solubility, you'll find that here we have much more solubility. So we will keep it a while and find out what would be the result. The same we are going to do with the para-amino benzoic acid sample. Okay, can you see it? Okay, so now we are going to add, okay, if you can notice that it's already soluble. Okay, all the particles are dissolved. So para-amino benzoic acid, it's highly reactable with the HCl. So we expect the basicity of para-amino benzoic acid to be much more than the paracetamol. Okay, now we are going to test for the tyrosine. So once again, we'll take 1 ml of HCl. and we will try to dissolve it. If you can notice, it's slower than para-amino benzoic acids, but it's for sure quicker than the paracetamol. If you can see now, I think the test tube is clear for you. It's now clear, but it takes time, which is more than the time needed by the para-amino benzoic acid. Now let's compare the three test tubes together, okay? Now we find that the para-amino benzoic acids becomes soluble quickly. It means there is high reactivity between para-amino benzoic acids and HCl, followed by tyrosine, followed by paracetamol, who's still trying to be solubilized by the added HCl solution. Okay, now we are going to proceed with the next part of this experiment, which is re-precipitation tests. And we are going to do that using sodium hydroxide, but I have to get the test tube closer to the camera so you can see the results very well. So here is the para-amino benzoic acid. It's soluble. And now we are going to add the sodium hydroxide. Of course, the content of the test tube here, it is para-amino benzoic acid and HCl. So now we are going to reverse the reaction, so please focus here. See, one drop only, it resulted into immediate formation of precipitates. Can you see it? It's very clear and obvious. Okay, so these are the results after reacting sodium hydroxide 2 molar with the result of reaction between HCl and the amine containing compounds. Okay, now we are going to proceed with the second sample, which is the tyrosine. Okay, now we have to do the same with the test tube that contains tyrosine after reacting with HCl. Now it is clear solution because the salt formed is soluble in the aqueous media. Now we are going to reverse this reaction by reacting between the content here and the sodium hydroxide. So once again, please focus with me and with the result. So see, I add 1 drop, 2 drop, 3 drops, more and more, and now it started to form. Can you see it well? It's here, apparent in the bottom of the test tube. Okay, so it takes longer time than para-amino benzoic acid. Now I'm going just to add more and more of HCl, and I found that is forming more and more. Okay, so now we're going to the conclusion. Stay with me, please. Okay, so after reacting the non-aqueous soluble amines, which are the tyrosine, para-amino benzoic acid, and paracetamol, after reaction with HCl, we got clear solution. Okay, and this clear solution, actually the rate was very high for para-amino benzoic acid, more than tyrosine, more than paracetamol. And even the paracetamol, if we can notice till this point, it's still trying to be soluble, but it is even more soluble than the paracetamol alone with water. Okay, now we reversed this reaction by reacting with sodium hydroxide. We found that the solubility or the precipitation or re-precipitation formation, it was more quicker with para-amino benzoic acids, again, more than tyrosine. This indicates that para-amino benzoic acids have more basic property, is more stronger base than the tyrosine, than the paracetamol. That's why the rate of the reaction was rapid with para-amino benzoic acids, more than tyrosine, more than paracetamol. After we are done with the chemical experiment, now we are going to proceed with writing the results according to the chart we just recorded. So we found that tyrosine, distilled water, it will be insoluble. The same for para-amino benzoic acid, it is insoluble. And the same for paracetamol, it is insoluble. for sure that results would be occurring because of the presence of benzene ring in all of them, which will reduce the aqueous solubility of the amines. While for diethylamine it was soluble. So that's why we will not proceed further with the diethylamine as we mentioned in the introduction. Okay, for the HCl solution, we found that with tyrosine, it will become soluble or it will form soluble salts. The same for para-amino benzoic acids. It forms soluble salt, and with paracetamol it will form soluble salt. But it is not the formation of the soluble salt the thing I'm looking for. I'm looking for the rate of the reaction. What is the rate of reaction or what is the rate of formation of the soluble salts? According to the experiment we had, we found that para-amino benzoic acid formed the soluble salt very quickly. So we will give the para-amino benzoic acid rank 1. Then tyrosine, which took more time, so we will give it rank number 2. And then paracetamol, which took longer time, so we will give it rank 3. So why we have such difference in the rate of the reaction? By the way, the same rate of the solubility or formation of soluble salts, it is the same rate here if we are going to proceed. Let's see it and then we will go back to the conclusion. For the sodium hydroxide, after addition of sodium hydroxide to the tyrosine, after formation of salts, we found that once again it becomes insoluble. The same for para-amino benzoic acid, it becomes insoluble. And the same for paracetamol, it becomes insoluble. And we are for sure excluding diethylamine from the beginning. Okay, once again, the reprecipitation occurs quickly with the para-amino benzoic acids, and then it occurs a little bit slower with tyrosine, and the slowest was with the paracetamol. Okay, let's understand why we got such results. If we went to the chemical structure of the amines, as we can see here, we will find that all of them contains nitrogen, and the nitrogen is the source of the basicity. And as we know from the electronic configuration of the nitrogen will have 2 electrons free, unpaired in the final orbital. So the same here and the same here. These 2 electrons will have a negative charge, and this negative charge will attract whatever protons are within the solution. So let's say that these 2 electrons will be responsible about the attraction of protons, so it will be responsible about the basicity of that nitrogen in each compound. Okay, for these 2 pairs of electrons, actually they will not be located in this site, because the nitrogen, as we can see, it is surrounded by 2 electron withdrawing group. Here we have the carbonyl group, and here we have the benzene ring. And both of them, we call them, or we classify them as electron withdrawing groups. So they will withdraw the 2 electrons from the nitrogen away. So this will result in reducing the basicity of that nitrogen. So this nitrogen will have low basicity. Okay? Next, we will go to that nitrogen in the para-amino benzoic acids. We found that this nitrogen, it's linked directly to only 1 electron withdrawing group, which is benzene ring, directly. So, in compared to the paracetamol, we will say this nitrogen will be more basic than the paracetamol. Why is that? Because the 2 electrons in both of them, in case of paracetamol, it's surrounded by 2 electron withdrawing groups, so these 2 electrons will not be available for attraction of protons from the surrounding media or the surrounding solution. While in case of para-amino benzoic acid, these 2 pairs of electrons are subjected only to the effect of 1 electron withdrawing group, so it will have a little bit higher basic property. Let's go to the tyrosine. This is the nitrogen of the tyrosine. Once again, there is 2 pairs of electron, and this nitrogen is surrounded by 2 electron withdrawing group. But if you can see the electron withdrawing group in that scenario, it's far from the nitrogen. One of them is far by 1 carbon, and the other is far by 2 carbons. So once again, it looks like tyrosine have the same scenario of paracetamol. But what is the difference between them? In paracetamol, the nitrogen is linked directly to 2 electron withdrawing group, while the tyrosine here, it's linked to two electron withdrawing group but indirectly with long methyl and ethyl bridge. So let's rank them according to the effect of the electron withdrawing group on the two pairs of electron. We will find that the highest effect is here, so it means it would be the lowest basicity in paracetamol. And then we found this one, it will have higher basicity than paracetamol, so let's give them a rank. This one would be the lowest. And this one will have slightly higher basicity, so we will give it rank number 2. While in case of para-amino benzoic acid, it's linked directly to one electron withdrawing group, so we will give it rank number 1. So this rank is ranking the basicity or the degree or the strength of the basicity. So the strongest base among these three is para-amino benzoic acid, followed by tyrosine, followed by paracetamol. If we are going to compare these results with what we got here, we will have the same rank. And this is very logical. If we have stronger base, it means the rate of reaction with the acid, it will be much more stronger and faster. And if you have weak base, so the reaction with the acid will be slower and it will take longer time for the observations to occur. So that would be all for today's experiment. Hope you enjoyed it, and I'm going to see you inshallah in the next experiment. Assalamu alaikum.